Good morning, everyone. Thank you for joining us today. I'm Kang Zuheng from Ping An Technology, and with me is He Yayun. We're excited to present our paper on Retrieved-Augmented audio deepfake detection. This is a new way for detecting the faked audios, but it uses quite different method. As you know, the Retrieval-Augmented based method has been successfully used for enhancing the quality of text generation. So, we borrowed this idea and propose our RAD framework. Let's dive into it. Next, let's talk about the background and our motivation. Detecting audio deepfake is the challenging task. But why? Because real audio recordings contains a lot of rich information. It's not just the voice itself, but also the background sounds and the meaning behind the words. On the other hand, the synthetic audio created by TTS or VC is generated by the models. Most of the time, these models do the excellent job and can produce an amazing voice, which works nearly perfect. However, for the audio deepfake detection model, there are many factors to consider. So that's why audio deepfake detection is very hard. Seen from the picture above, the traditional method always rely on a single model. It could be pipeline or end-to-end approach. However, this method has a fundamental flaw because the audio data is too complicated. It is too hard for one model to make a good judgment. To solve this, our motivation is pretty simple. Let's use external knowledge. For example, if I want to detect the audio sample with speaker A's voice, we can gather many voice recordings of speaker A in advance. Then, we carefully compare the test audio against all the recordings of speaker A. This difference guides us to make a much better decision. Okay, let's imagine a scenario like this. Your friend brings you a computer with this logo and say, "This is my MacBook." But you invite a person born in 1900 and ask him, "Is it real or fake?" He'd probably say, "I don't know." But what if he had read a book about all the logos in the world today? He may first pick out these two most similar logos, and then compare them carefully, and then find the flaws in that logo. Now he can answer you, "It must be fake, because it is too thin here, and there's no dots there." So with this motivation, we propose our RAD. Before introducing RAD, let's review the well-known RAG. This method greatly improved the generation quality of large language models and reduced the hallucination. It contains 3 stages. Stage 1. Build knowledge database. Firstly, we cut text into chunks. Then, we convert all the text chunks into vectors. Then, we can build a vector database for retrieval. Stage 2. Retrieve knowledge. When a user asks a question, then we can search and retrieve similar knowledge from the vector database. Stage 3. Generate answers. We can build a prompt based on both users' question and the retrieved knowledge. Then LLM will help us generate a good answer. For RAD, it has similar structure of RAG, but it's a little bit different. For the stage 1, we cut audios into chunks here because our task is to detect fake audios. For the stage 2 and 3, both of the test sample and the retrieved sample will be sent to the detection model. Finally, this model can make our final decision. For experiment, we train our model only on ASV spoof 2019 dataset and test it with the ASV spoof 2019 and 2021 test sets. To enhance the performance, we use the additional VCTK dataset to build our database for retrieval. For evaluation metrics, we use EER and mean TDCF. From 2 tables above, we can see that on ASV spoof 2019 and 2021 test set, our performance is slightly better than before and reaches the state-of-the-art performance. This means that our RAD framework breaks the performance bottlenecks. This table shows the ablation study. We mark them as different colors. For the green row, with our complete framework, we reach the state-of-the-art performance. The red row shows the RAD can further improve the performance than the single model for detection. The blue row shows the additional data for retrieval can help the model make better decisions. The purple row shows the fine-tuned wave LM can largely improve the performance. So in conclusion, our proposed RAD framework provides a new perspective that uses more available information to overcome performance bottlenecks in audio deepfake detection. Experimental results shows that our method reaches the state-of-the-art performance. Our work opens the promising research avenue into retrieval augmentation-based technique to enhance the performance for detection tasks. Thank you for listening. If you like our paper, please cite us. Thank you. Here are some photos from the conference that we can look at.